Morning. Boker tov lekulam. Good morning. It's really exciting. I mean, the room is full. Two little women, isn't it? All the women. Can you stand up? I want to make it an announcement. Okay, so good morning. I can see you anyway. I would like to take a minute and introduce myself. I'm Professor Michal Lineal. I'm the director of the Israel Institute for Advanced Studies. And it's really a pleasure to open this conference on proof of geometric Langlands conjectures. And you know, I'm a neuroscientist and a molecular biologist, and I can even consider myself a computational biologist. But everything, despite the fact that I like interdisciplinary and multidisciplinary, nothing can prepare me to talk about your conjecture. So I apologize for that. Actually, mixing fields, it's something that is very close to my heart as a scientist, but also to the heart of the IIAS, the Israel Institute for Advanced Studies. Actually, this is the essence of what we are doing here. And I've discovered over the past year or so, in which from the moment that I was positioned to this quite exciting, I must say, position, is that one of the most fun part is really to open such a meeting. And the reason being is that always I take it as an opportunity to learn something that I know nothing about or little about. And, you know, just a nice trick to expand my own kind of knowledge. You know, over this last year, I gave an introduction for biblical reading, for Jewish text, for Kant experimental thinking, including also synapses and Banach spaces and all this. But I think you are challenging me, really. I mean, far more than any of the previous ones. So. Even with the Banach space, I was able to say something meaningful, and not talking about the recent school that we had on quantum informatics, which was quite nice. But so what I did, of course, I went to, actually some of you may know that I'm living the last day, I don't know, 40 years with a mathematician. So always, this is very good, you know, with Nati. And, but he was not at home, he was at yoga. So what should I do? So I opened the internet and went to the wiki, you know, maybe something clever that I can say. And it was very embarrassing. Really, I couldn't understand the word. I mean, there was something about duality and some models, some conjecture, some triangular view, some categorization, and even number theory. Which I felt on safe ground. But, you know, and I said, well, I'll just take the first explanation words in Wikipedia, you know, supposed to be for the public, isn't it? So it starts by saying, let's X be a smooth and complete curve over, and G a reduction graph. We let G denote the length total graph. And immediately it's go to categorization, geometrical, conjecture, and that's it. I lost it. And it's all with blue. You know, if you don't understand the word, go there and go there. So I said, okay, I'll stop here about your topic. And I would just end by saying that many of you probably, or some of you, do not know much about this institute. So now I'm really on a safe ground. And you know, the Institute is a place that was initiated or started already at 1975 with one goal, which is to have a place in which new idea can be planted and innovative solutions can be, you know, formulated and personal interactions will be supported. That's it. End of story. And as you arrive to begin your conference today, I really hope for you to do this wonderful science to get a little bit further towards the solution or towards the understanding. I like even the title that you're not really telling us about the conjecture. You just take us a step forward, which is kind of nice and modest. And today really marks the culmination of weeks of work, of preparation and dedication of many, many people. I won't go over the names, but just to mention that our staff, that was really fundamental in doing it, your organizers and everybody around this institute. And I really hope for you a very pleasant few days. I want to take just to say specific thanks to the organizer, to Dima, to Dennis, to David, of course, and to Yaakov Warshawski. Without you, it won't happen. It wouldn't be possible. And thanks for everybody that comes to Jerusalem, to Israel, to Jerusalem, and to this institute. And Bruchim Habayim. Purim Sameach.
So I think when Dennis and I scheduled this talk as the first talk, we were expecting more people to be jet lagged and not come. So it's going to be kind of weird.
That's why it's hard categorizes.
Yes. And well, maybe people are jet lagged, but they just showed up, so then they can sleep.
Are you jet lagged?
What?
Are you jet lagged?
I am also jet lagged, yes. I am Sam. Dennis is exerting his influence throughout this entire conference. So the title of this tutorial, and we'll sort of find out what the difference is between a tutorial and a talk is in the next hour, is higher categories for humanities majors.
Like this Wikipedia page.
This will be, I'm sure, at a much lower level than any Wikipedia page. So I just kind of want to make a couple of general points about the structure of higher category theory. So this is a subject that we're going to be using throughout the week very freely. As far as I understand, it's assumed as a prerequisite for the conference, which means I don't actually need to communicate any information right now. And I have no intention of doing so. But I want to just kind of explain a perspective on the thing that makes its use natural, because I think there's a tendency to look in some of the literature on higher category theory and think that, oh, it requires thousands of pages of reading to learn how to use it, and it's very complicated, and what's it even good for anyway? So I want to just say that it's very natural, and then we'll see during the week more what it's honestly good for. Yeah, and so the title of this lecture, by the way, is a reference to the fact that I learned these ideas from a talk David Kazdan gave here when we were all in Jerusalem in 2010 for biblical scholars who were also at the Institute at the same time. And he was tasked with explaining what we were doing to them. And he explained it by analyzing a poem by Wallace Stevens and explaining basically the ideas I'm going to say. So I want to say that there are some problems with traditional set theory that I want to give a just vague sense of how they're corrected. And we'll see that just as soon as you correct these problems, you've invented infinity categories. So there's like one, oh, and a warning is that I know nothing at all about logic. I apologize if I say anything wrong or stupid. Like that's kind of the subject of the talk, and I really don't know the thing. So okay, so the basic like verb in set theory is equals. So you have two elements of a set. You ask yes or no, are they equal elements? Or you have two sets. You ask yes or no, are they equal sets? So what does it mean that they're equal sets? Well, it means all of their elements are equal. So it's a thing that's trained out of you as a mathematician to ever think about this. But it's really annoying because, for example, there are many sets with one element. So there's the set containing the empty set, and there's the set containing the empty set. And you're told, as like when you really do set theory, to really think these two things are different sets. There's like no mathematical test you could ever perform that would distinguish between these two sets. And like in practice as a mathematician, you forget that there's more than one set with one element. But in set theory, which like we take as the foundations of mathematics, this is a real thing. And it leads to lots of annoying problems. Like, you know, the definition of category, you say you take some set of objects, but there's no real set of objects of a category because like that's not preserved under equivalence, which is really how you're supposed to think about categories. It's only up to equivalence. So I don't really know how to use these chalkboards. OK. So there's whoops. There's a school run by Voevodsky now that is trying to teach something called homotopy type theory, which is supposed to be new foundations. I also haven't studied this, so I can't comment too well on it. But the idea is to replace the notion of equality. So like as the basic unit of sameness in mathematics. So the idea is to use like isomorphism instead. So this is one possible word for the notion. People might say homotopy, or they might say well, just one way to kind of spell it out is that instead of two things being yes or no equals, someone has to tell you how two things are equal. So here, there's a canonical way of saying that these two sets are equal. So, you know, there's exactly one way, but, you know, in practice as a mathematician, like if someone gives you two vector spaces and an isomorphism between them, there's no longer any test you can perform in mathematics that will distinguish between, at least in linear algebra, that will distinguish between these two vector spaces in the absence of additional structure. Like, there's just nothing at all you can do. So this is the whole idea. So if you've ever looked at this stuff, there's this fancy word, univalent, that they use. And univalent, as far as I understand, means there's no mathematical test that can distinguish between two things that have been identified. So just, well, so there's a funny fact that like this has been the, you know, the foundations that everyone learns as a student. So I want to say this is kind of a historical fact. Like when you think like the foundations of mathematics were being developed 100 years ago, and people were coming at it with like, you know, they wanted to give like firm foundations to the real numbers, to the continuum, to like the abstract notion of a group, and to finite fields, or you know, whatever. Like, and set theory is like extremely great for letting you make those kinds of problems, you know, like make those constructions rigorous. But it's like you do algebra for a little bit and you realize like, oh, the tensor product's only defined up to unique isomorphism, and that's a kind of annoying feature of set theory. Like it doesn't really adapt to a lot of that framework so much. So this is meant as some kind of replacement. I guess I'll just So I want to say that now, if you take this seriously, the concept that emerges to replace sets is that of what should be called infinity groupoid. It's like the basic unit of structure in mathematics. So what's the reason? Well, like the verb equals is now just banned from your life. So what could you possibly say like about mathematical objects? Well, like so like how do mathematical things organize now? So they're like there are objects, So you can construct different things. And then if you are given two objects, you can ask for ways to make them the same. But now, if you're given sort of x and y and some way of identifying them, well, you can ask, so you can think sort of f1 or f and g. These are two different ways of identifying x and y. You can, moreover, ask for identifications for ways of identifying f and g. In other words, there's no concept anymore of saying that two isomorphisms are equal. There's only the concept of saying that two isomorphisms have been identified. And once they've been identified, there's no mathematical test you can perform that will distinguish f and g. But before that, and they may not even be the same, right? Like they could be different sort of automorphisms of something. But that then, reaches more seriously. So this kind of extends indefinitely. You can ask for different ways of identifying different ways of identifying different ways of identifying. And that's the infinity and infinity groupoid. So just in case you haven't seen the idea of infinity groupoid before, the idea is a 0 groupoid is a set as we know it. A 1 groupoid is a groupoid as we know it. And higher groupoids are supposed to be, well, exactly this kind of structure. So that's kind of the point. Is as soon as you have just remove this verb equals from your life, you immediately have higher category theory emerging. So this doesn't follow the usual patterns of mathematics where you say oh, here's a bunch of axioms. How do you define things in mathematics? You write down a bunch of sets. You write down a bunch of structures on these sets, which are some maps between other sets. And then you ask that these satisfy some properties. And there are various ways of realizing the world of infinity categories inside of the world of sets by those properties. And all of them are extremely complicated, whereas the language that you end up using is extremely simple, or reasonably simple. And there are kind of two options. One of them is you write down a really, really complicated set of axioms, which if you've ever looked at the literature on two categories, people write down complicated definitions, and then they check that lots of properties are satisfied, and it gets very complicated. Or you can have a simpler set of axioms, like Jacob Lurie uses in his book Higher Topos Theory. It's a reasonably simple set of axioms, but it's almost impossible to write down any non-trivial examples without appealing to difficult things, or the real numbers or something, and geometric realizations of simplicial sets, which seem irrelevant to these kinds of purposes. So I want to say this will be kind of the way we use the language. So you can interpret this in different ways. One of them is you can say this is, there are different ways of modeling the theory of infinity categories, and the language we're using is model independent. Another perspective you can give is that this Svobodsky school needs to finish its project on redoing the foundations of mathematics. And once they do that, this language will have been implemented and will be obvious from whatever axioms they have and from, well, their work on rigorous foundations. So yeah, so now once you have infinity groupoids, the next level of structure that replaces categories is infinity categories. So the way you should think about these are just that you have, again, collections of objects. x, y, etc. And you can form Hom between x and y, and this should be some infinity groupoid. OK, so now the convention that'll be enforced throughout the conference, given these facts, is we'll just call infinity groupoids as groupoids. We'll call infinity categories as categories, etc. So if we want to refer to, if for some reason we want to refer to the old notion, then we'll say 1, category. So generally, people use NM category. The phrase NM category means that you're allowed kind of morphisms up to degree n, and you require that past degree m, something like that, they should all be invertible. So a 1, category is your usual notion of category. A 2, category is your usual notion of 2 category, and an infinity 1 category is what I'm calling an infinity category. So an important characteristic feature, which is sort of the major difficulty in using this stuff in practice if you were, like, for example, trained in algebra, is that you can't use formula anymore. So I think there were a lot of students in my middle school math class who would be really glad to hear you can't say equals, you can't use formula anymore, but what's the question?
That's not exactly.
What does you mean? What does it mean?
That you can't use formula, but well.
Yeah. So I'll kind of I want to try and spell this out. So you're used to, in some ways, just like writing down a formula for something. Like a common example is like the differential for some chain complex. You just write some complicated formula, and then you check that when you like compose some maps that it satisfies whatever properties you want. And it's just like it's kind of not allowed anymore. It doesn't really make sense because what you traditionally are doing is you're checking that two things are equal at the end of the day. So you need to think more in terms of like someone telling you that they're equal. So like a kind of typical example for this is that you should think like, what's an algebra structure now? So what you're used to is a map from A cross A, or let's say A tensor A to A, that satisfies some properties. So you just check that it's associative. Whatever, there should be unit, this kind of stuff. So instead, what you're supposed to take is that you have maps from A tensor n to A for, well, for each integer n, and you require various compatibilities between them. So like, for example, the condition of associativity is something about some property from A, like that two maps from the third tensor power of A to A are supposed to be equal, and that's not allowed anymore. So instead, you have to, someone has to tell you how those two maps have been made equal. So what was that? Yeah, it's something that the language lets you do. So yeah, so I want to give some sense for how that's done, like what you can possibly do to replace formulas, but that's, you have to get used, like it takes some practice to just get used to like what's allowed and what's not allowed. And hopefully by the end of the week, everyone will have a good sense for that. But like a typical annoying example is like, well, this is a conference about geometric Langlands. You want to talk about D-modules on things. So you're used to saying like a D-module on, say, a smooth variety is like it's some sheaf of abelian groups that has an action of functions, is quasi-coherent as such, and has an action of vector fields that satisfy the Leibniz property. And you sort of can't do that in this world. So Dennis will explain an alternative in the next talk.
Can you just explain this line? It says you're not allowed A tensor A to A, instead A tensor N to A? What's the difference?
Well, I want to say it's not just a property of, so in like usual algebra, you write down a single map from A tensor A to A, and you check that it satisfies some properties. So what I'm saying here is that like instead you should sort of think that like for starters, one thing you have is that there are two different ways of constructing maps from the third tensor power of A to itself. And you require that someone has told you how to identify these two maps. And
Yeah, it's more.
it's more data, yeah. But see, it's a real difference, because what you would have done in classical algebra is say like, here's my formula for the multiplication. Let me just check that it's associative now. And that there's no analog of that idea anymore. So you have to find this algebra structure as like emerging, for example, from some functoriality or as endomorphisms of something. It needs to be, guaranteed by the formalism, as opposed to like you write down a formula and check it. So it's too bad, but so the substitute is you use lots of limits and colimits. This is sort of your major operation for constructions. It requires thinking in a different way to retrain, like, the constructions you used to be able to do by hand, you have to call by a limit or colimit now, and then you can get to do them in this new world. So let me just explain briefly what this means. So here's an example. So if you have some maps x, z, and y, a diagram in C, so C being some infinity category, then what does the fiber product mean here? Well, usually the fiber product means like giving a map to the fiber product is the same thing as giving maps S to x, s to y, such that the corresponding maps to z are equal. So that's not allowed anymore. So instead what we do is we take maps to x, maps to y, plus an identification of the induced maps to z.
What does it mean, identification?
Well, like this is our basic predicate now. Is you can say I've made two things equal. I've identified two different things. So it means isomorphism, for example. It's this looser notion. Any other questions? So this is a basic example of what people call maybe homotopy limit a lot of the time, which means a limit in some kind of homotopy theoretic setting, where homotopy theoretic setting is interpreted as basically as inside of an infinity category. So more generally, given some functor f from I to C, so these should both be infinity categories, the limit of f is, well, the limit may or may not exist, but it's some object of C equipped with compatible maps and from the limit of f to f of I for every object I and I, and it's universal with respect to this property. So the notion of compatible here is a little bit more fraught than it is in usual category theory. So here, it resembles this picture. So like compatible doesn't mean equals. It means that you specify the additional data of identifications between two different things. And that's the characteristic feature of a homotopy limit. So
sorry, what is VT there? Given f from I to C.
uh-oh. Given f, oh, between.
Oh. So can you say what is not, I mean, this looks like standard category theory. What is the difference here? What are you saying is new?
No difference.
But then, no, I don't know.
Well,
So, yeah,
So-
it's true from usual what? Is that all?
okay, so in
The difference is what means compatible.
yeah, the difference is what compatible means. So the issue is I'm sort of postulating some foundations that don't really exist quite yet. So I like, if you push me enough, I'll resort to like, I can say, oh, quasi-category is Jacob's book, something, something, and give a precise definition out of there as a way to say it. But I want to make a different point here, which is like, so in usual category theory, well, basically my experience of it is that, it's helpful as an organizational principle, but it rarely teaches you anything you didn't already know. Like you can sort of perform every construction you already want, and okay, sometimes it happens to be a limit or co-limit, but who really cares? You just write down some product and some subset of that product that satisfies some properties, and you've done your construction. And no one ever needed to tell you the word limit or co-limit. And here, I want to say this is the only way of doing a construction like that, is to call it a limit or co-limit. So that's somehow the only point I'm making, is that like there are going to be lots of limits and co-limits written during the week, and you could be like, but what is this thing really? And the answer is you don't really have such a good concrete description of it in the terms you're used to. The only terms you have are limit and co-limit anymore. And you have like formal ways of manipulating these things that like miraculously turn out to be enough to actually prove the theorem you want to prove. But yeah, no, I mean, there's, when you think in these terms, the use of higher category theory is like trivial. I mean, it's easy to use once you get used to the restrictions. Does that at all address your question? Yeah, so again, you have co-limits, which are certainly dual to this. And just, well, a few other like words that are just going to be used a lot during the week. So I like, yes?
Universal has also different meaning in this setting from the, because universal before was also something like equal.
Universal is the same thing as limit and co-limits.
Yeah, so
Yeah, but before, universal meant there exists a unique map, and now you have
no.
like, universal here means something.
Yeah, okay, so unique and canonical and these sorts of words, well, okay, canonical maybe has no meaning. Unique has a precise meaning. So like you think everything organizes into like these higher groupoids. So a particular example of a groupoid is a set. So no surprise, these are the groupoids in which there's at most one way of saying two things are equal. There's at most one way of saying two equalities are equal. There's at most one, so on and so forth. And so you have a singleton set just as well. And to say that something is unique means that like some infinity groupoid is the singleton set. So yeah, so universal means like up to that kind of identification. And yeah, so any other questions?
Would it be enough to know as black box instructions the notion of a functor and the notion of a joint functor?
Pretty much.
Because your limits and co-limits are...
Yes, that works.
Basically, if you know as black box how to compute limits and co-limits, like see there's risk for mistakes, because like, well.
Can you give maybe a simple example of an infinity groupoid, which is kind of a good example?
Okay, so it's one of the basic principles here is that infinity groupoids are like that homotopy theory, as you learn it in whatever a first-year graduate course, is modeled on infinity groupoids. So like any topological space, for example, gives rise to some infinity groupoid, where you're supposed to think that the points of the topological space are the objects of your category, paths between two points are. So that's one way to say it. I mean, or you could take, well, I mean, you can draw complicated diagrams that do it, but usual categories are good examples of groupoids. Yeah.
Just say for a fundamental groupoid of topological space. That's the basic example you want to think about. Points, paths, what's up.
Or I mean, you can say, see, you get stupid. Okay, here's the kind of mistake you could make. So you can take the push out of a point with a point over point union a point, let's say in the category of pointed spaces. So in the category of and this is the homotopy type, which is like the circle. So this is the kind of mistake you'll make if you forget that we aren't working in the higher categorical world.
In pointed spaces, the joint union of point is point.
Well, I mean this groupoid considered with either one of its points as a base point. Okay, it's meant to, like, it's supposed to be the suspension of S0, like the suspension of the zero sphere. So considered as a pointed thing. Other questions, comments, concerns? Yeah, so just other terminology. So a category C is, so at this point I'm basically just setting up conventions. So it's co-complete if it admits all co-limits. And yeah, so a basic example here is that groupoids admit all co-limits. If you're careful, then categories admit all co-limits. And now a useful construction is that if you're given some functor from some category to some other category, and a functor here to D, where I assume that D is co-complete, then there's some, actually I can just call it f. There's some operation called left con extension of f. So it can be, well, it's, if you know usual left con extensions, then you know this. So you can think in terms of the formula left con extension of f evaluated on some object x is the co-limit under the data of y, some object of c naught, and then a map from I of y to x, right, a map in C, co-limit of f of y. So this satisfies a universal property. So for example, it's not clear that there is a functor that's given by this formula. I mean, you can sort of just like push it through and make it work. But since we aren't allowed to write formula anymore, you have to be more careful than you once were. Like back in the day, you could just say, OK, I send objects to this, and I send a morphism between two objects to this, and then just check that it preserves composition. So that's the sort of thing you're not allowed to do anymore. So instead, it's better to think in terms of like what universal property does it satisfy. So the answer is that there's a canonical map from f to take the left con extension and then restrict it via the map I to a functor. So it's a natural transformation as functors from C naught to D. And this left con extension is universal, well, is initial with respect to receiving such a in other words, given some functor from C to D and a natural transformation like this, then a natural transformation from f to the restriction of that functor, there will be a sort of unique induced map from the left con extension of f to g that fits into a commutative diagram, where now commutative diagram is a structure, not a property. So yeah, actually saying the word initial object, maybe this addresses Dragosh's question better about what's universal. So universal typically means initial in some category or final in some category. And let's say initial in some category means that every time you map to some other object, like the groupoid of those maps is the contractible groupoid. In other words, the singleton set. So that's one notion that'll be used a lot. Why do we, you care more about left con extension and right con extension in higher category theory because you have fewer options available to you. Like, what are you ever going to do to write down a functor? You can't use formula anymore. The answer is basically like somehow you construct something by some formal procedure, and then all you can do is extend it by some other formal procedure. And it turns out this, people like to advertise sometimes that lots of constructions are left and right con extensions that maybe you didn't think of in those terms, and great. But it's useful in this kind of stuff because that's your only interpretation of lots of functors. Question?
Can you give an example of such situation?
There will be lots of them in Dennis's next talk. He nods. Well. Yes, Dima.
Is it fair to say that this situation is more complicated than what we're used to, and so some particular general operations like limits, con extensions were worked out, and it was in the sense that the formulas, that things were written by formulas in this particular example, in one particular setup. And so now we can keep using them because we know that they work.
Yeah, so it's again like the different ways of making kind of precise what this talk is about. So the key way that I would always fall back on if I were forced at gunpoint is like, aha, you know, I know Jacob's book, I know what's in it, and he gives particular meaning to all of these words and proves these theorems, assuming like ZFC. And so you can say that, you know, using that stuff he is like constructed by more or less explicit formula most of the time, ways of doing this. Explicit formula and whatever, axiom of choice.
I'm just trying to understand that it seems to me that in principle you can write things by formulas. It just seems completely like a total waste to do it in every case, and that's why we fall back on these general constructions, and these are the tools that we are using.
So the way to write things by, okay, the method to write things by explicit formula is to say like, okay, there's some notion of model category, which presumably people are broadly familiar with, but it's meant to be like, you know, okay, what you learn in algebraic topology at a first pass is like, you know how to compute the homotopy fiber product of spaces, namely you replace something by some path space that's homotopy equivalent to it, and just to make some map of fibration. And you say, aha, okay, if I systematically replace things according to some general principles, then I'll be able to compute all of my homotopy limits and colimits by explicit formulas inside of this model category. And it is a well-defined thing to a certain point. But the thing is, like, the categories we're going to be working with all week are, like, there's no way to do that if you just write down some random colimit of DG categories. Like, that just doesn't exist to you anymore. So in some ways, I want to advocate the picture that it's just like it's not allowed anymore. Because once you get used to the fact that you can't do that in the categories of interest anymore, then so you accept some degree of foundations, and where these foundations come from, you can have different perspectives. So one perspective is that they're explicitly worked out by some formulas and according to mathematics as we usually know it. And another perspective is that, like, you know, well, you accept ZFC, and you've always accepted this. You might as well accept this better thing. And, well.
ZFC can be explicitly formulated. And what you are presenting is not an explicit formulation.
Absolutely, yeah. Yeah, no, it's...
Of course, it's better to ignore, but somehow.
But see, I know that CFC can be explicitly formulated, but I couldn't possibly do it.
Yeah, it's a detail.
No, but see, I have belief that, like, in a couple of years, these guys will completely work this stuff out. And, I mean, they seem headed that way. So, fine. You know, I'm in a bad position for a couple of years. And not that bad a position, because I also know how to set this up in CFC. And you don't need to worry about, like, see, you know it's correct mathematics because it can be set up in CFC. So you know, you can check every proposition in Jacob's book, and you're in good shape. You never need to worry that you're, like, doing voodoo instead of mathematics. But other questions?
Well, maybe rather a comment if you allow.
Sure.
I think sometimes you can actually try to use formulas in the sense that you can define some notions which are more strict in the sense that they require more equality than the others. For instance, even for quasi-categories for the model of Jacob-Ruby, you can have different notions of an adjunction which are all equivalent, but one of them is like the usual to categorical adjunction. You can work with it for formal reasons, but then you will pay for that later in the sense that you cannot have all monads with such adjunctions properly. So maybe you can say that you can write formulas, but this, well.
But see, if you okay, as soon as you start using explicit models, you run into a number of provisos. So that's like one kind of proviso, but anything you say, there will be a like, but you have to blah, 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 blah. And if you just remove that notion of strictness from your life in the beginning, then there are no buts. Every statement you want is true. It's like, it's true as stated. And okay, every true statement you, whatever, reasonably true statement you want is true. And like there are no provisos. You don't need to worry about like, is it good enough? Well,
this will explain that the series have no chance to exist.
What is it?
What you say is precisely probably explains that the series has no chance to exist. Because you have to work, you know. It's not that you remove all the properties by saying nice words.
No, yeah, right. So I mean, the point of this is like.
For example, formal equation. In critically, there is one technical important problem that if you have a two, instead of working equality, you say up to contractible set. And there is a real issue that it's an intersection of two contractible set doesn't have to be contractible. But there is
no yes, but so.
Intersection. So
yeah. Okay.
This is precisely the reason why the infinity categories cannot be obvious.
No, okay, so first of all, you're making two different points at the same time, so let me respond to them one at a time. So I'm not saying that like this does mathematics for you. What I'm saying is that there's an extensive literature on how to work with model categories, which is very foreboding and complicated, and doesn't like prove theorems for you either. So I want to say that this is a much easier to use framework that lets you just like skip ahead and actually like do your mathematics and prove your theorems. So I'm not claiming that this like magically proves theorems for you. I'm just saying that it's easy to use and like you worry less when you're actually trying to prove your theorems. So that's one point. The other point is about some intersection of contractible sets. And see, I know various ways of making sense of what you're saying. So one of them is to say that the fiber product of two contractible things over something might not be contractible. And fine, we agree. No one ever said it was. And the other way I can make sense of it is just to say like within the world of topological spaces, which you might regard as equipped with a particular model structure, modeling infinity groupoids, sometimes you compute your homotopy fiber products wrong if you do it. And again, I agree with you, but this is exactly meant to remove that kind of thing. Like, see, when you don't work with explicit models, you don't make mistakes like thinking that the intersection of two contractible sets is going to be contractible again. Like, if you form your intersection correctly, then it's not an issue. Other questions? Dennis, time. Okay. It's enough. Thank you.